Hey, welcome to the normal curve section. Talk a bit about a few distributions and what you need to know about them, and that will wrap up our statistics for this unit. And that'll wrap up the units for the course. Woohoo! Can't believe you made it this far, right? Isn't that fun? All right, so we won't talk about the normal curve first, we'll talk about that last. But when you're looking at a histogram, remember those from a few lessons ago? Sometimes you'll find that your data will fit particular distributions. In other words, sometimes you'll find that your histograms fit a certain shape. Not all the time, but sometimes. And some of those shapes have names. Rectangular, J-shaped, bimodal, skewed, normal. There's all kinds of different ones that have names. And we're going to go through some of those and what the shape looks like and where it might come up regularly. All right, first one is something called a rectangular distribution. And it's exactly what it sounds like. If you're looking at your histogram and you see that all the bars in the histogram are the same height, in other words, you're seeing that the bars all have the same frequency, then your classes all have the same frequency. And when you look at the histogram, the bars make basically a rectangle, kind of a rectangle shape if you outlined it. This might happen, for example, if you are looking at the frequency that you roll each a 1, 2, 3, 4, 5, 6 on a die after lots of rolls. So like you just say you roll the die 100 times and you keep track of how many times you land on a 1, how many times you land on a 2, how many times you land on a 3, etc. And you use the 1, 2, 3, 4, 5, 6 as your classes and how many times you land on them as your frequencies, you should get a rectangular shape distribution in that case. Okay, next one is J-shaped. I have a hard time seeing why it's called J-shaped. Basically, you're going to see histograms that steadily climb either up like stairs or down like stairs. Forgive my drawing here, I know it's terrible. But they call that J-shaped. I can almost imagine sort of a J being drawn in here somehow, but I don't know. You got me as to why they're really called that. But they're constantly increasing or decreasing. Okay, can't last. Sometimes I can kind of erase that or ignore this, but other times it's like, well, if somebody's trying to read this later, they're not going to be able to read that. Constantly increasing or decreasing. An example might be the number of hours studied per week by students. You might have lots of students who study 0 to 5 hours, fewer that study 6 to 10 hours, even fewer that study 11 to 15 hours, and so on. The more hours, the more study hours there are, the fewer students you'd probably have doing that. So it would probably be a steady decline in frequency or how many students are studying that much time. So that can be an example of a J-shaped distribution. Bimodal, you'll see your histogram and most of the bars will be kind of close to each other, but then suddenly you'll see some bar that shoots way up. Redraw that, sorry. Suddenly you'll see some bar that shoots way up. And then you'll see some more bars that are kind of clustered close to each other or whatever. And then you'll see another bar that shoots way up. I'm having a hard time drawing. So it kind of reminds me, it's like, to me, I like to call this the Wolverine one. Although Wolverine had, what, 4 blades coming out of his hands, or 3? But still, it's kind of, I feel like, it kind of reminds me of Wolverine with like the blades sticking out. But bimodal, you'll have 2 non-adjacent values occurring more frequently. So non-adjacent, so it won't be side by side. They'll be occurring more frequently than others, than all the others. For example, let's say you're charting men's and women's weights on the same histogram. Well, you're going to have, for women, they're going to have a certain weight that occurs the most often, and that would be one of the bars, probably this one right here. And then men will have a weight that occurs the most often among men, and that'll be another bar over here. And all the other bars will be lower and kind of occurring not as frequently. And down here is a mix of women's and men's weights represented. So you might have 2 separate modes because of men and women being 2 separate genders and having different weight information. That's just one example. Skew. Skew is another type of distribution you might have. Your histogram for skewed left would start out kind of look like stair steps. And then it'll dip down suddenly. And then your histogram for skewed right will kind of quickly go up and then gradually go back down. Like that. If you draw, like sometimes with distributions, instead of drawing with the histogram bars, they might draw it with this nice curve. The curve represents what's going on with the histogram bars. Like if you take the tops of the histogram bars and connect dots, you can make the curve. That's how you kind of represent with curves. So skewed to the left, the humps over towards the right, skewed to the right, humps over here towards the left. An example maybe of, let's see, number of children might be, per family might be distribution skewed to the right. There's a few examples, number of children per family. You'll have a few that have 0 children. You'll have more that have 1 children. Maybe the greatest number have 2 children. Fewer than that have 3. Fewer than that have 4. And as you get to more children, the number of families with that drops off. Very few families have 15 or 20 children nowadays. It's just not something we do nowadays. So that might be a skewed right. That's an example of a skewed right distribution. Now, the things with these distributions, the reason they're skewed is because something's happening with the averages. Let's say I give a test. Or no, let's say that we're looking at your grades. I'm just making, I don't know, I don't have, this is not a particular student, but let's say, let's say you've been working really hard, but it seems like all you can pull is mostly C's. But then suddenly Well, you're okay. No, I'm gonna do skewed left first since it's on top. I was thinking more skewed right. All right. Let's say that most of your grades are really high. So like right here, this is the peak of the histogram. This is the mode. So your grade that occurs the most frequently is over here towards the right. And it's pretty high, so you're making like A's or B's pretty frequently. But then let's say you make one low grade. Remember, the mean is affected by those lower grades, by those extremes. So let's say suddenly you have a really bad day and you come in and make a C or D on a test. But what that's going to do is it's going to skew your average. It's going to pull it, instead of being completely over here on the right, nice and high, it's going to pull it some towards the left to make it skew towards the left. And then now the middle is going to be dragged down too, and it's going to be right in here. So your mean is less than your median, which is less than your mode. So an example might be lots of high grades, but a low grade skews the mean to the left. Whereas down here, maybe somebody had lots of low grades, and then they made a higher grade suddenly, made it like 100. Well, that's going to skew their grade to the right, skew their grade a little higher. So that's going to pull their median, or I mean their mean to the right. And then the median's always in the middle. So in that case, if it's skewed right, that means some value over here in the extreme right is starting to pull it over. So instead of being this nice little mountain here on the left, some value over here drags it over, stretches it out, so that your mode is less than your median, is less than your mean. So if you've had lots of low grades and suddenly some higher grade skews it to the right, then your average, grade average, goes up. Your mean is now higher than your mode. Your mean average is higher than their grades that appeared the most often. And something like that happens. Okay, then the normal distribution. Well, for those of you who are education majors, I don't know if classes still did this, but when we were back in school, they taught that all grades should fit a normal curve, a normal or bell curve. This is also called a Gaussian distribution, named for Carl Friedrich Gauss, famous mathematician, who was also a very eloquent writer. If you ever get a chance to read a book about him, you might be able to have the privilege of reading some of his love letters to his wives. Yes, I said wives, plural. Back then, women died a lot, so. All right, so the normal curve. What's happening with the normal curve is that your mean, median, and mode are exactly in the center, and they're equal to each other. And it's a mirror image. The left side is a mirror image of the right side. And your mean, median, and mode are smack dab in the middle here. So that's the normal curve. It's not skewed. It's not, certain other shape. Just it looks like a bell. They used to say, oh, that's how grades should be. Most of your grades should be C's here in the middle. You should have an equal number of B's and D's, but fewer than the number of C's, and then the equal number of A's and F's, but even fewer than all the others. That was the theory back then. And that's when they talk about grading on a curve, that's when teachers are trying to force that bell curve. Like if students do super bad on a test, and they try to force that bell curve by adding points or doing something to unskew it. Although you don't really hear about teachers doing anything if everybody made A's. So I don't know. I don't think the bell curve is necessarily a good thing, depending on what's happening in the class. If nobody's doing their homework and they all fail, well, teacher curves, then that's not an accurate reflection of what the students did or know. Anyhow, so this normal curve, some things about it. The graph of the normal distribution is a normal or bell curve, which I just showed you. And the curve is symmetric about the mean. I just talked about that, normal or Gaussian distribution. The mean, median, and mode are equal. I just talked about that. And it's right there, smack down in the center. It's like that line of symmetry. And then something called the empirical rule applies. I haven't talked about that yet. There's something called standard deviations, which we haven't covered and we're not going to get into in this book. This is the only place you need to worry about standard deviation. If you take a stats class, you're going to be doing a lot with standard deviation and looking at areas under the curve. But what we're doing for now is just memorizing the empirical rule. It's saying if you have a bell curve or, you know, like a histogram that follows that whole normal distribution, then a standard deviation is an equal amount to divide up your curve. It's a set width to make divisions in your curve. And there's formulas for figuring out what your standard deviation should be, like what that width should be when you're divvying up your curve into parts. But once you've figured out your standard deviation, one standard deviation to the right, one standard deviation to the left. So that width to the right, that width to the left here from the center. It's saying 68% of your data should fall in that area. So your histogram, the frequencies for the bars here, should cover 68% of the data. Then if you go further out to 1, 2 standard deviations, 1, 2 standard deviations, then 95% of your data should fall within there. And if you go to 3 standard deviations, 1, 2, 3, 1, 2, 3, remember that's 3 below and 3 above, then 99.7% of your data should fall in there. Then there's these little, they call them tails, these little pieces on the ends that don't quite touch the ground. 0.3% of your data will fall in those tails. So 0.15% here in this tail and 0.15% there in that tail. And those are the extremes. All right, so memorize that. Know that rule, because that's basically how you'll be tested on it. Like knowing what percent of the data falls 1 standard deviation above and below, what percent falls 2 standard deviations, what percent falls 3 standard deviations. Just know that the 68, 95, and 99.7 is the empirical rule. But let me give you a real world example of what this means. Let's look at IQ scores, intelligence quotient. And we can think about IQ scores. According to IQ scores, like when they measure IQ, most of the population falls here in the middle with IQ of 100. Okay, so the mean IQ score for the human population is 100. The standard deviation is 15. And they take their data and apply their formulas. They figure out that the standard deviation is 15. Okay, so if we start dividing this up, if you go 1 standard deviation to the right, you have an IQ score of 115. Because that's 15, the standard deviation is 15, so 100 plus 15. If you go 1 standard deviation to the left, the IQ score is 85. because that's 100 minus 15. That's the mean minus the standard deviation, minus 1 standard deviation, and the mean plus 1 standard deviation. If you go 2 to the right, I don't know why it's doing that. I don't want that little line there because that's going to be confusing later. Just trying to draw lines, people. All right. So you go 2 to the right, you add another 15 for your standard deviation, and you got 120. If you've gone 2 to the left, you subtract another 15, and you end up at 70. 3 to the right, add 15, you're at 135. 3 to the left, subtract 15, and you're at what, 55? Okay, so according to the empirical rule, what's happening here, now the mean is 100, that's the average. 68% of the population IQ scores are 85 to 115. So if your IQ score is somewhere from 85 to 115, then you are part of 68% of the population. Because that's this part right here. That's 68%. 95% of the population IQ scores are 70 to 120. So if you're somewhere from 70 to 120, hey, that's cool. You're part of 95% of the population. And that 70 to 120, that 95% includes the 68% that was in here, plus that additional 27%. So you got 13.5% and 13.5% covered in these two little rectangle area, like these two little areas here. Then finally, 99.7% of the population IQ scores are 55 to 135. So most of the population, except for extreme few, fall somewhere from 55 to 135. So 0.3% are outside of that. 0.15% is below 55, so that's your unfortunate souls who have significant brain retardation or something going on there. And then 0.15% over there above 135. So now you're starting to get into genius territory. And that's rare. Because if 99.7% falls from 55 to 135. So that's the empirical rule for you. That's a real life example of applying the empirical rule. So memorize that. Memorize those percents and remember which percent goes with how many standard deviations below or above the mean. And that will cover it for the empirical rule. And that actually covers it too for the course. We're done. I appreciate you sticking with me on this journey. I'm glad you were able to stick it out and learn all this. Good luck preparing for your last test and your final exam, and I hope to see you again sometime soon.